I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss one more important topic in the fifth module of engineering physics course, that is waves in one dimension. And what we are going to do in the topic, we'll discuss. We have already discussed about oscillators. This is the first part in this module where we have discussed about simple harmonic oscillators, damped harmonic oscillators and forced oscillators. I can say this is part 1, harmonic oscillations. Now we are going to go into the next part, that is waves in one dimension. So in waves, we are first going to discuss about these transverse and longitudinal waves and waves equation on a string. So let us see the brief outline of how we are going to discuss this topic. First, we will try to understand what a wave is and see the basic classification of waves. Then we'll discuss about the definitions of terms that are involved with waves. So what are the important terms and what their definitions are? We are going to understand very clearly. And then we'll discuss in detail about longitudinal and transverse waves. Then we'll derive an expression, a general wave equation. It will be applicable for both longitudinal as well as transverse. And then we'll be deriving individually for longitudinal as well as transverse wave. First, we'll be deriving the general wave equation. Then we are going to derive an expression for the velocity of a transverse wave. What will be the velocity of a wave when it is a transverse wave? We are going to derive. So let us first understand what a wave is and what is wave motion. A wave is formed due to the disturbance caused in the medium. Any type of wave you consider, whenever there is a disturbance that is caused in the medium, the wave travels forward. So a wave is formed due to the disturbance that is caused in the medium. And whenever a wave is formed, it transfers energy from one place to the other without transport of matter. The matter may not move. It may just vibrate about its mean position, but the energy is propagated in the forward direction. That is what happens in wave motion or wave propagation. Here we are seeing a simple example. If you consider a still pond of water where the water is still, you just drop a pebble in the water. Then wherever the pebble is dropped, surrounding it you have waves. You can see in the picture, there are waves that are formed. So, and the wave propagates forward in all directions. If you see how the wave propagates, this is the origin of the disturbance where the pebble is dropped. And this disturbance is carried forward in all directions. So, you can see the waves propagating in the forward direction. Now coming to the classification of waves. First is mechanical waves. What are mechanical waves? Waves resulting from the physical displacement or a part of the medium displaces from equilibrium. Then we have mechanical waves. The second one is electromagnetic waves. So what are electromagnetic waves? Those waves resulting from the exchange of energy between electric and magnetic field. So whenever we talk about electromagnetic waves, there is exchange of energy between the electric and the magnetic field. So the waves that are resulting due to this exchange of energy, we call them as electromagnetic waves. Then the third kind we have matter waves. Matter waves are associated with wave-like properties of elementary particles like the electrons, protons. So whatever elementary particles we have, the wave-like properties of these elementary particles, we are calling them as matter waves, and they are a different kind of waves. Now coming to the classification of mechanical waves. When we consider mechanical waves where a part of the medium is vibrating, we have again they are classified into two: transverse waves and longitudinal waves. So what is a transverse wave? In a transverse wave, the particles of the medium vibrate perpendicular to the direction of motion of the wave. So let us take an example of a string. We take a string AB which is tightly held between these 2 points A and B. Means there is tension in the string. Now if the particles of this string vibrate perpendicular like this and the wave is moving forward in this direction. The wave is moving in the forward direction. The particles of the medium vibrate perpendicular. Perpendicular means at right angles. So they are vibrating at right angles. Then you call it as a transverse wave. So in a transverse wave, what do we have? We have crests and troughs. They will alternate each other. So the crest means displacement, maximum displacement in the upward direction. You call it as crest. And the maximum displacement in the downward direction, we call it as trough. So the displacements will be like this here. And they alternate each other. So this is one complete wave. We can say one crest and one trough will make a complete wave. So as the wave propagates forward, there will be a number of crests and troughs and they alternate each other. Now coming to the longitudinal wave. So what is a longitudinal wave? Where the particles of the medium vibrate in a direction parallel to the direction of wave motion. So if you consider this is the direction of wave motion. If I consider the string, I consider a string which is tightly held between 2 points A and B, means there is tension in the string. Now when it is plucked or it's given a jerk, then what happens? The particles of the string may vibrate parallel. So this is the direction of propagation of the wave. This is the direction of wave motion. Wave motion, or I can write it as direction. Direction of wave motion. And how are the particles vibrating now? They are vibrating parallel to the direction of wave motion. So then you say it's a longitudinal wave. So in a longitudinal wave, we have compressions and rarefactions. So compressions means where the particles come closer together. And where they are apart, we call it as rarefaction. So when the particles are vibrating parallel to the direction of propagation of the wave, there are some regions where the particles will come closer together. We'll see it in a simulation. So where they are coming closer together, we call it as compression. And where they go apart, we call it as rarefaction. So in a string, if you see, these compressions and rarefactions will alternate each other. So again, after one compression and rarefaction, there will be again a compression, rarefaction, and so on. Now let us see. In a longitudinal wave, how are the particles vibrating? If I am considering a string, what we see here is a thin one. This is the string. And these balls represent the particles of the string. These balls represent the particles of the string. Now, how are the particles or the balls vibrating? They are vibrating about the mean position and it is parallel to the direction of propagation of the wave. This is the wave propagation direction. This is how the wave is going forward. This is the direction of the wave. So how are the particles vibrating? That decides what type of wave it is. So here they are vibrating parallel to the direction of motion of the wave. So we call it as longitudinal wave. Now coming to the transverse wave. So in a transverse wave, the particles, how they are vibrating, if you see at any point of time, these particles vibrate perpendicular to the direction of motion of the wave. This is the direction of motion of the wave, and the particles are vibrating up and down at right angles, or we say perpendicular. So this gives a clear idea of how the particles of the medium vibrate in a longitudinal wave. They vibrate parallel to the direction of propagation of the wave, and in a transverse wave, they vibrate perpendicular to the direction of propagation of the wave. Now, if you see the wave as a whole, in a longitudinal wave, the particles vibrate parallel to the direction of motion of the wave, and as the particles vibrate, the wave is propagated forward in the forward direction. Now, for a transverse wave, if you see, the particles vibrate perpendicular. So, this is how the wave, a transverse wave, looks like. Now, what we understand here is different terms we are going to see. If this is a wave that is formed, a transverse wave, because of the vibrations of the particles. So, in a transverse wave, we have crests and troughs. Crest is the displacement in the upward direction, you call it as crest, and in the downward direction, you call it as trough. So, in a wave, in a transverse wave, we are having a series of, this is crest, trough, crest, trough, crest, trough, and so on. That is what we call a series of crests and troughs. And the distance between two consecutive crests or troughs, we call it as wavelength. Wavelength is the distance between two consecutive crests or two consecutive troughs. That also gives us the wavelength. Now coming to longitudinal wave. So in a longitudinal wave, how the particles are vibrating? They are vibrating parallel. Parallel, this is the particles are vibrating like this to the direction of propagation of the wave. This is the direction of propagation of the wave. So this is definitely parallel to this. So when this happens, what we are observing, at some positions, the particles come closer together, and at some regions, they are apart. So where they are apart, we are calling it as rarefaction, where the particles are apart. And where they come closer, we call it a compression. So compressions are regions in the wave where the particles are closer together. And in rarefaction, they are away from each other or they are separated. So what do we see in a longitudinal wave? We see a series of compressions and rarefaction. So compression, rarefaction, compression, rarefaction, compression, rarefaction, and so on. So this is the clear picture of what we understand about a transverse wave and a longitudinal wave. Now coming to the examples of mechanical waves. First we'll see longitudinal waves. So when you are speaking on a mic, the sound propagates in the form of longitudinal waves. Clapping, when we clap, so when you are clapping, the particles of the medium will vibrate parallel to the direction of motion of the wave. So you call them as longitudinal waves. The same thing with the vibrating drum heads. So when you beat the drums, there also the vibrations are parallel to the direction of motion of the wave. And also the music woofers which we use in the sound system. So all these which we see in our day-to-day life are examples of longitudinal waves. Coming to transverse waves, the best example we know is light waves. Light waves are transverse in nature because the particles vibrate perpendicular. We are talking about electromagnetic waves. Light waves are electromagnetic in nature. So the electric and the magnetic components, they vibrate perpendicular. And then the ripples in a water pond. So when you are dropping a pebble in water, the ripples that are caused give rise to transverse waves, where the particles vibrate perpendicular to the direction of propagation of the wave. Then the plucking of a string in a guitar. So when you pluck the strings in a guitar, what happens? They will vibrate perpendicular to the direction of motion of the wave. And same thing with an oscillating string or a rope. So if you take a string, stretch it tight in between 2 points, means there is some tension in the string. Then you just vibrate it and leave it. It vibrates perpendicular. So we call it as transverse waves. Now, in both the modes of propagation, means in transverse as well as longitudinal waves, the particles of the medium vibrate. So they vibrate about their mean position simple harmonically. So that is how we are relating the harmonic oscillations with waves. So what is happening here is when the particles of the medium are vibrating in both the cases, in transverse waves as well as longitudinal waves, they vibrate about the mean position. They are not displaced from the position. They are just vibrating about the mean position, and that motion is simple harmonic in nature. We have already discussed in detail about the characteristics of simple harmonic motion. So all characteristics of simple harmonic motion are applicable to waves, because in wave motion we are seeing simple harmonic motion of the particles. So all characteristics are applicable to waves also. Now let us see some terms that are involved in discussing about the waves. So the first one is displacement. So displacement is the distance traveled by the vibrating particle at any instant of time from its mean position. So suppose we have a wave. So at any point of time, I can find the distance traveled by the particle. Say at 0.5 seconds, we are plotting a graph for time along the x-axis and displacement along the y-axis. Means as time varies, the displacement also varies. So at any point of time, you see the position of the particle. So the distance traveled by the particle at any given instant of time, we call it as displacement. And it is always measured with respect to the mean position. Means if I have to calculate the distance here from here to here, if I have to calculate the distance or the displacement, say at 4 seconds, it is here, always with respect to the mean position. So I consider this is the mean position. So at any point you can calculate the distance. Now coming to amplitude. The maximum displacement of the particle on either side of the mean position is known as amplitude. Means if I see here, the maximum displacement it has in the upward direction is here. So this is the amplitude. Amplitude denotes the maximum displacement in either direction. Here you are seeing in the upward direction and here it is in the downward direction. So this is also called as amplitude. So the maximum displacement. Here the displacement is not maximum. And here also it is not maximum. If you see the displacements and compare, it is the maximum here. 4 is the maximum displacement. The same way if you see here, 4 is the maximum displacement. So the maximum displacement is always called the amplitude, and it is with respect to the mean position again on either side of the equilibrium position or the mean position. Now coming to velocity. So what is the basic definition of velocity? The rate of change of displacement with respect to time. That gives us the velocity. So how do we calculate the velocity of a wave? So we will start with the displacement. If the displacement of the particle is given by y is equal to a sine omega t plus phi. Y is the displacement at a time t. We have seen just now, as time varies, the displacement varies. So at a particular instant of time, we are writing the displacement is y. And it varies with time, and this is a sinusoidal function. So y is equal to a sine omega t plus phi. A here represents the amplitude. We have already discussed amplitude is the maximum displacement from its mean position, and omega is the angular frequency. Omega is angular frequency and phi is the initial phase. Phase always talks about the state of vibration of the particle. So suppose the particle is starting from the mean position, we may consider phi to be equal to 0 and simply write the expression as y is equal to a sine omega t plus phi, in case the initial phase is equal to 0. So y is equal to a sine omega t plus phi. Now if you have to find velocity, velocity is dy by dt, rate of change of displacement. So we'll take the derivative of this with respect to time. A is a constant. So for sine, it is cos. So because phi tends to 0, I will not write phi. So for cos sine omega t, it is cos omega t into omega for omega t. So I can write it as a omega cos omega t. So the velocity is given by a omega cos omega t. Now we can also write in terms of sine, because we know sine square omega t plus cos square omega t is equal to 1. Sine square theta plus cos square theta is equal to 1. The trigonometric properties we know. So now if I have to write for cos omega t, so cos square omega t will be 1 minus sine square omega t, or cos omega t will be under root 1 minus sine square omega t. So we are going to substitute for cos omega t under root 1 minus sine square omega t. So we have a omega. So a omega as it is we are writing, and for cos omega t, what we are substituting? Under root 1 minus sine square omega t. So a omega under root 1 minus sine square omega t. Now from here we can write what is sine omega t equal to? Y upon a. So sine square omega t will be y square upon a square. So 1 minus y square upon a square. So can take the LCM. So a square minus y square upon under root a square. So we can write it. B is equal to a omega under root a square minus y square upon a square. So a square under root we can take it outside and write it as a, and here we have a square minus y square. A and a will get cancelled. So we are left with v is equal to omega under root a square minus y square. So we have v is equal to omega under root a square minus y square. Now this is the formula we are going to use for velocity at any point of time. V is equal to omega under root a square minus y square. Now one more thing we need to understand is when will the velocity be maximum. So now if you consider a simple pendulum, this is the equilibrium position. So as it vibrates, this is one complete oscillation. So here if you see, the velocity is maximum. Once it goes to the extreme position, the velocity becomes 0. So here at the equilibrium position, the velocity is maximum. So what is the condition we have for maximum velocity is x is equal to 0. So if you substitute for the displacement y, here we call it as y is equal to 0. So when y is equal to 0, what you have omega under root a square. So this will be a. A into omega is a omega. So the maximum velocity is given by a omega. Now coming to acceleration. What is acceleration? It is the rate of change of velocity of a particle with respect to time. So a is equal to dv by dt. So what is v here? We know y is equal to a sine omega t. So v will be equal to, v is equal to dy by dt. So y is a sine omega t. Take the derivative of sine omega t. It is cos omega t into omega. So v is given by a omega cos omega t. So if you have to find the acceleration, it is the rate of change of velocity dv by dt. So it will be d by dt of a omega, capital A we are taking as amplitude, a omega cos omega t. So a is equal to, I'll write the constants outside. So derivative of cos is minus sine, and for omega t we have omega. So we can write it as minus a omega square sine omega t. So the acceleration is given by minus a omega square sine omega t. And what is sine omega t from here? Sine omega t will be equal to y upon a. So let us substitute for sine omega t y upon a. So this is equal to minus a omega square y upon a. A will get cancelled. This gives us minus omega square y. So the acceleration is minus omega square y. And when is the acceleration maximum? The acceleration is maximum at the extreme position. So the condition is y is equal to a, the maximum displacement, which is called as amplitude. When the displacement is maximum, the acceleration is maximum. And the maximum displacement is denoted by amplitude a. So for y, we are going to substitute a. So we get a max is equal to minus omega square a. So a is equal to minus omega square y we use. And we also find a max from here. Now coming to frequency. The number of waves produced per second gives us the frequency. It's a very simple definition. What is frequency means? How many number of waves are there per second? That gives us the frequency. And time period here is the time taken by the particle to make one complete vibration. Okay. So if you are talking about a particle which is vibrating about the mean position, so it starts from here, it goes up, comes down and comes back. So that is why we are calling it as simple harmonic motion. Here I am talking about a particle which vibrates perpendicular starting from the mean position. So the time it takes for one complete oscillation, this is one complete oscillation, one to and fro motion is one oscillation or one vibration. So the time taken for it is called as time period t. Or we can also define it in other words, like the time taken by the wave to travel one wavelength distance. What is the time the wave takes to travel one wavelength distance? That also we call it as time period. So if you see here, this is the wave. Again, we are plotting it for time along the x-axis versus displacement along the y-axis. So one period is what? the time taken by one complete wave, one wavelength of the wave. This is one wavelength. One crest and one trough gives us one wavelength. So the time taken by the wave to travel one wavelength. So this is the time taken for one wavelength. So we will call it as time period T. So this is the time period T. Now what is wavelength? We are going to see different definitions for wavelength. The distance between any two crests or troughs. You call it as wavelength. Or the distance traveled by the wave by the time the particle completes one vibration. So the particle is vibrating about in the main position and the wave is traveling in the forward direction. What is the distance the wave travels by the time the particle completes one vibration? Also we call it as wavelength. So you see here, so the particle you see here is vibrating like this. So by the time the particle makes one complete vibration, the wave travels through one wavelength distance. So this is one wavelength. Otherwise, what we are calling the distance between any two crests or troughs. So what is this distance? Distance between any two crests. This is a crest, this is a crest. So the distance between any two crests, we are calling it as wavelength lambda. So I hope you understand both the definitions. The same way you can talk it about the distance between two troughs is also one wavelength. Distance between any two troughs or any two crests is called as wavelength, or you can write it in other words, if the particle vibrates like this, the wave propagates in the forward direction. So when the wave propagates forward, what is the time taken for one complete vibration? And what is the distance traveled by the wave during that complete vibration? We will call it as wavelength. Now coming to angular frequency. Angular frequency is the time rate of change of phase. Phase always talks about the state of vibration of the particle. So how the phase changes with respect to time. We are calling it as angular frequency. If I have to write a generalized formula, omega is equal to theta upon t. And for one complete vibration, the time taken is the time period. And in one complete vibration, it turns through an angle of 2 pi, 360. So we write omega is equal to 2 pi by t. For all derivations, we use omega is equal to 2 pi upon t. T here is the time period and 2 pi is the angle through which it moves. So phase is the state of vibration of the particle. So here if you see, what is angular frequency? By the time the particle completes one vibration, what is the angle through which it is moving? 360 degree. What is the time it takes? T, the time period. So we are writing 2 pi upon t. Now wave number. Wave number is denoted by k. So in all expressions we are going to use this wave number k. So let us try to understand what is this wave number. The number of waves per unit distance. How many number of waves are there in a given unit distance? If you can count, that gives us the wave number. And if you have to express it mathematically, it is expressed as the number of complete cycle of a wave over its wavelength. So k is given by 2 pi by lambda. Lambda denotes the wavelength and 2 pi is a angle. So k is equal to 2 pi by lambda. And then what is wave velocity? The velocity at which the disturbance moves through the medium or the wave moves through the medium, we call it as wave velocity. And the wave velocity is given by v is equal to n lambda. A very, very important expression. V is equal to n lambda, the velocity. V represents the velocity. N represents the frequency. and lambda is the wavelength. So we understand here how velocity, frequency and wavelength are related. V is equal to n lambda. In some cases, we may denote frequency by f also. Suppose we are using, for number of waves, we are using n. And in such case, for frequency, we may use the notation f. So we can also write it as V is equal to f lambda. F is the frequency here. Now let us compare and contrast transverse waves and longitudinal waves so that the picture of the differentiation becomes very clear. So in transverse waves, the particles of the medium vibrate perpendicular to the direction of propagation of the wave. This is the basic difference between transverse and longitudinal waves. Particles vibrate perpendicular to the direction of propagation of the wave. Here the particles vibrate parallel to the direction of propagation of the wave. And in transverse wave, we see crests and troughs. Crests are the maximum displacement in the upward direction. Trough is the maximum displacement in the downward direction. And longitudinal waves consist of compressions and rarefactions. Compressions are regions where they come closer together and rarefactions where the particles are apart. And in a transverse wave, there are no variations in pressure and density of the medium, because when the particles vibrate, they vibrate perpendicular to the direction of motion independent of each other. So what happens here is there are no pressure or density differences in the medium through which the wave moves. But in case of longitudinal, there are variations in pressure and density. If you see, for example, at compressions, the density is more because the number of particles per unit volume is more. So there are variations in density. At compressions, the density is more, and at rarefactions, the density is less. Now, transverse waves can be propagated through solids and surfaces of liquids, but not in gases. You do not see transverse waves passing through gases. But here, if you see longitudinal waves, they can pass through solids, liquids and gases. So, example, light wave, and here it is a sound wave. Now, let us come to the expression wave equation on a string. We are going to derive an expression for a wave equation on a string. Means we take a string and tie it at both the ends. This string is fixed between 2 points A and B, tightly held so that there is some tension in the string. So when you pluck this string and leave, there are waves that are formed. You will see waves like this moving in the forward direction. Always you see here at this is the string. Always at the fixed point, you will have a node. Now, the displacement of the particle is given by y is equal to a cos kx minus omega t. So, we are writing y as a function of x and t. X is the change in position and t is the time. So, as time varies, the position of the particle varies. Or if I have to put it in other terms, if the position is different, the time is also different. So, we are writing y. So, the general expression for displacement of a wave is given by y of xt is equal to a cos kx minus omega t. So, a is the amplitude. K here is the wave vector. We have seen k is equal to 2 pi by lambda. And omega is the angular frequency, which is given by 2 pi upon t. So now how do we get the wave equation, a generalized equation for any wave on a string? So first what we are going to do, because there are two variables x and t, first we are going to differentiate it with respect to x. So we are going to do the partial differentiation. So whenever there are two variables, I am going to first differentiate it with respect to x. So dou y by dou x of xt means t here remains constant. So whatever the terms that are there with t, they remain constant. So all this you must have done in your mathematics. So the same thing we are going to apply here. So dou y by dou x of x of t will be what? What is the expression we have? A cos kx minus omega t. So for cos kx minus omega t, we get minus sin kx, because the derivative dou y by dou x, if you talk about dou by dou x of sin x, will be cos x. And for cos x, it will be minus sin x. These are the basic formulae we know. So the same things we are using here. So dou y by dou x will be A cos kx minus omega t into k. For kx we get k. So we are writing minus k sin kx minus omega t. Now we are going to find the second derivative, dou square y by dou x square. Take the derivative of dou y by dou x. So whatever is constant we keep outside. We have here minus ka. And for sin kx minus omega t, we get cos kx minus omega t. And for kx we have k. So k into k will give us k square. Minus k square into a cos kx minus omega t. Let us consider this as equation 1. So let this be equation 1. Now we are going to take the derivative with respect to t. We are going to see what is dou y by dou t. So dou y by dou t will be omega a sin kx minus omega t, because the derivative of cos, I'll write here dou y by dou t. If I have to find, a is constant, and for cos kx minus omega t we get minus sin kx minus omega t, and for omega t here there is a minus, so we get into minus omega. So there is a minus here and a minus here, so we are going to get plus a omega sin kx minus omega t. So what we are writing, dou y by dt is equal to omega a sin kx minus omega t. Now let us take the second derivative, dou square y by dou t square. So we are going to take the derivative of this with respect to t. So what will be the derivative of sin omega a is a constant now. And for sin kx minus omega t we get cos kx minus omega t, and for minus omega t we get minus omega. So we have minus omega here, so we'll have minus omega square a cos kx minus omega. So that is what we are writing here, minus omega square a cos kx minus omega t. So let this be equation 2. So dou square y by dou x square is 1, dou square y by dou t square is 2. Now we are going to substitute equation 2. From equation 2, we will substitute the value of a cos kx minus omega t. So what is our equation 2? Dou square y by dou t square is equal to minus omega square a cos kx minus omega t. This is our equation 2. This is our equation 2. So from here, we should get the value of a cos kx minus omega t. So what will be a cos kx minus omega t? Simply I'll bring this minus omega square here. Because it is in the numerator, it goes to the denominator. So I get minus 1 by omega square dou square y by dou t square. So from equation 2, we are getting the value of a cos kx minus omega t. Now we have to substitute this in equation 1. So what is our equation 1? This is our equation 1. No? Dou square y by dou x square is our equation 1. So in this, for a cos kx minus omega t, we are going to substitute minus 1 by omega square dou square y by dou t square. So what will be the expression? If you substitute, you already have minus k square here in the numerator, and here we are getting minus omega square dou square y by dou t square. So minus minus will get cancelled. So we are left with k square by omega square dou square y by dou t square. Now let us make the substitution. K is equal to 2 pi by lambda, which is the wave vector, and omega is equal to 2 pi f. You can write it as 2 pi upon t or 2 pi f. Now we want k square upon omega square. So how do you get k square by omega square? What is k square? If I have to write k square by omega square, our k is 2 pi by lambda. So whole square upon omega is 2 pi f whole square. So 2 pi by lambda whole square will be 4 pi square by lambda square. And in the denominator we have still 4 pi square f square. 4 pi square will get cancelled and we are left with 1 upon lambda square into f square. 1 upon lambda square into f square. And what is lambda f equal to? V, or V is equal to f lambda. So if you have to see here, what is V? V is equal to f lambda. So in place of lambda f, we are going to substitute 1 by v square. So what will be our expression now? Dou square y by dou x square will be equal to 1 by v square dou square y xt by dou t square. So this will be the final expression. This will be the general expression which holds good for all waves, not just sinusoidal waves. For any type of wave you take, this is the generalized expression for waves. I hope this is clear. We will stop here and we will continue our discussion in the next class. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.